Question time from you guys. What do you guys got? Victoria. Which section? 5.3, number 27. Would love to. The 5.3 questions are such a joy compared to some of the 5.2 stuff. All right. So the directions here were to just evaluate the integral. With the way this is currently written, do you have the tools that you would need to evaluate this? No, because you have the product of two functions, right? What am I going to do what am I going to do first then? FOIL it out.
Oh my God.
Yeah.
That's all I have to do. That really is.
So if I do that, then I can evaluate each one of those term by term. So the antiderivative for u squared is u to the third over 3. Antiderivative of u is u squared over 2. The antiderivative of 6 is 6u, evaluated from 0 to 1. So 1/3 minus 1/2 minus 6 minus 0 minus or plus 0 plus 0, which is just whatever that comes out to be. I don't really, at that point, I'm done. You know what I mean? Let you deal with the arithmetics. But that's the trick, is that had to do a little bit of massaging on that function to be able to integrate it, but not too bad. What else you guys got? Happy to do some more? Sure. It's going to be almost the same trick. Because again, if I look at the function here, I have the quotient of two functions. Don't have any antiderivative rules to handle that. So what am I going to do? Well, I'm going to think about it as two separate fractions. So that becomes that. And then now I'm ready to antidifferentiate. So what does that become? X to the 3 over 2 and then 2/3 minus 2x to the 1/2. So let's see. 9 to the 3/2 is 27. 18 minus 3/6, and then minus 2/3 minus 1. Oops. Plus. So again, taking a little bit of, doing a little massage to that function before you got started, and allows me to just be able to use my basic anti-differentiation rules, which is massively helpful. Jack, what's up?
Number 73.
Sure, same section?
Yeah.
Sure. I think these are some show that questions, which are always scary. Okay. So show that this is true. Now, if you look at this, is this true? Is 1 less than or equal to the square root of 1 plus x cubed? Well, definitely, right? Because provided x is greater than or equal to 0, you're always going to be adding, you always have a little bit more than 1. Square root something more than 1, it's going to be more than 1. So that's good. And then is the square root of x plus, or I'm sorry, is the square root of 1 plus x cubed less than or equal to 1 plus x cubed? Again, provided that x is always positive. Well, yeah, if I take the square root of something that's bigger than 1, it's got to be less than whatever you started with, right? So I'm convinced of that. That would be something I would explain in words, to be honest with you, just like the conversation we've had here. Sergio? Sure. Jack, are you happy with what we did there?
Yeah, that makes sense.
Okay. So for part B, what I'm going to use is this theorem from, it must have been section 2. Let me go find it here real quick. This is the one that I want. I'm going to be, oops. What am I? Okay. Let me just grab that. Just stretch you out a little bit, homie. All right. So if I look at these three, which one looks like the one that I need? Yeah. So all I'm going to do is say, okay, I take part A, and I'm going to integrate, because I know that that, oops, is true. Now, oops, forgot dx. Okay. This part is easy. That's a 5-2 property right here. So that's a constant. Integral of a constant is just going to be the constant times b minus a. And I still have this guy. And then this is just a regular old problem. So the antiderivative of x, or of 1 is x. The antiderivative of x the fourth is x the fourth over 4. I evaluate that from 0 to 1. I have 1 plus 1/4 minus 0 minus 0. So that is just 1.25. We're done. Because this is 1. That's it. So the harder part was part A, making that argument, but it's just like, how do you make that argument? And I would just make like a words argument on that. I don't think I would try to do that symbolically. It feels like that's just going to be tedious or something. Yeah, of course.
So just one side equal to 1 and then one side equal to 5.
Because that's what it wanted us to show, right? If I look at part B, the question says show that 1 is less than or equal to that integral, which is less than or equal to 1.25. So I said, okay, I just took part A, integrated all the parts, which I can do to hold the equality, or hold the inequalities, and then I just evaluated the two ends And I get 1 and 1.25. The questions at the end of this chapter weren't so bad as some of the end questions from previous sections. Victoria.
Could you do 69?
Either that or you guys are just getting better at them. Could be both, right? I do think you guys have made a lot of progress already. 69, sure. Is this, am I in the right section? That's right, okay.
Yeah.
Okay. Evaluate the limit by first recognizing the sum as a Riemann sum for a function defined on 0, 1. Okay. So let me double check and look at this. I think I know what it's asking us to do, but like those directions are rather cryptic. Let me just.
It worked.
That's how it always goes, Sergio. You take something down to IT and the walk down there fixes whatever it was. Yeah, okay. That's what I think. All right. So what it's basically trying to tell us to do is to rewrite this so that we can write it as an integral and do the integration rather than like the crap we had to do in section 2. So the key here, the key thing I'm going to notice is that I have like I cubed, but I have n to the 4th. So what I would do is I'm going to start by writing this as that. Where I've just rewritten, instead of n to the 4th on the bottom, I've wrote it as n cubed on the bottom times 1 over n.
Why did you put like all of that?
Well, because I want this guy is going to look like a delta x to me. Right? Where I have 1 minus 0 over n. That looks good to me. Particularly since it says that we're on the interval 0 to 1. So I know that's like my A and my B. This, then, I want to rewrite so it looks like a function of my xi, which is going to be a plus I times delta x. So in this case, that's going to be 0 plus I times 1 over n. Or just I over n. So that's easy. I can just write it as I over n cubed. So this is now like the limit as n goes to infinity. That's pretty terrible penmanship, Kulik. I equals 1 to n of f of xi delta x, where xi was I over n, delta x is 1 over n, and f of x is x cubed. So that's the integral from 0 to 1 of x cubed dx. And that's easy to do. So it's just 1/4. because that looks like my xi
Oh,
to the third, right? What's happening to xi is f of x, right? That's all.
then how did you get x to the fourth?
I took the antiderivative. I did the antiderivative of x cubed. So I just did I just integrated. Again, even unpacking this from here to there, I think was considerably easier than the 5-2, right? Even if I took this thing and had to rewrite it as an integral and then did the integration, I think is a considerable upgrade versus what we were doing in 5-2. Particularly once you've done it once or twice. And I think this back and forth, like converting between integral and like limit of sums or limit of sums back to integral, I think those are good 5-2 kind of questions where I don't ask you to actually evaluate the limit or do any of that nonsense. I just want to get some practice going back and forth between the forms. That feels like a pretty fair and doable test question to me. So what I'm saying, Victoria, would be like that part of it, where you've gone and taken the sum and written it as an integral, or taken the integral and written it as a sum. Those feel like good test questions for 5-2, where we get the idea without having to like grind through a bunch of terrible algebra. Does that feel okay? Okay. Anybody else? Okie dokie. 5-4. We're going to be talking about something called an indefinite integral. So remember in section 5.3, the fundamental theorem of calculus part 2 says that we have this definite integral of f of x is the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a. And that's true for any antiderivative of f, i.e., we're going to pick when the constant is 0. Since we can pick any antiderivative, let's just pick the one where it's 0. What we're going to look at in this section is going to be the indefinite integral. So the way we tell the difference between them is the definite integral has bounds on it. Indefinite integral doesn't. And the indefinite integral is just the antiderivative. Since it's not any antiderivative where we have our choice, it's just the antiderivative. What do we need at the end of these? Plus c's. Just means we have plus c's. Okay? Just like we did when we had in section 4.9 or whatever when we did antiderivatives last semester. Okay, so if I wanted to do the indefinite integral of x squared, that's going to just be the antiderivative of x squared, x cubed over 3 plus c. And you can check that by differentiating, and you get, again, x squared, because when you take the derivative of a constant, you get 0. All right. So here in this table, I've collected, or we've just collected our antiderivative rules and rewritten them as integral rules, just for I don't know. Yeah, kicks. Sounds good. So the first three here are like rehashes from section 5.2 or whatever when we saw these. But everything else is just like repurposing the antiderivative rules from last semester. So not a lot new here, right? Everybody's cool? Hopefully we still remember these. They are super handy. From here on out, we're mostly just going to be doing some examples now. So these integral examples are going to get a little bit more complicated in this section, but still can be done with just your antiderivative rules. Yes?
Why did you cross out above?
Because they're hyperbolic equations that we didn't do hyperbolics on AB. I don't think it's a BC topic even. So these hyperbolic trig functions were what those were. That's sine H and cos H, H being for hyperbolic. So if you're on like, instead of like a flat surface, you're doing it if it's like a curved surface. Doing trig on. We're not doing that. But that's why I crossed those two out. All right. So I'm going to do this first example like real by the bookie and show like all the steps of kind of what's going on. And then we'll kind of streamline the process here a little bit. But I think the first time through, it's important that we're seeing like, what is Mr. Kulik doing to get this antiderivative out of here? Everybody's cool with that? So first thing I'm going to use is this property over here that allows me to distribute my integral. And notice since that entire function is in parentheses with the dx outside, there's a dx on each integral. Everybody's good there? Okay. Next thing I'm going to use is, what's up? It's not subtracting. Oh, yes, it is. Okay, thank you. 100%. The next thing I'm going to use is this first property, where if I have a constant times my function, I can pull that constant out front of my integral. The very first one on the list. They didn't number them for us because that would have been too convenient for me to reference. Need me to move up? It's okay, you can ask. It's no big deal. Okay. So now let's go ahead and do our antiderivatives. So I'm going to have 10 times, and then the antiderivative of x to the fourth is x to the fifth over 5. Very good. And then what do we need to have after it? Plus c. And then we'll have minus 2 times the antiderivative of secant squared is tangent. Good. And what do we need to have after that? Plus c. Now notice that technically speaking, I probably should have done this, right? Everybody agree with that? And technically speaking, these should be different c's because they're not necessarily the same constant. But what do I get if I do 10 times some arbitrary constant? What do I get? I just get a constant, right? And if, well, we're getting there. We're getting there. And if I want to add C1 and C2, if I add two arbitrary constants, what do I get? Still just get a constant. So I'm going to reduce that fraction over there. So the way I would write my final answer would just be plus C. because C1 plus C2 is still just another constant. We're just going to package them both together and call it C. So if we look at really what we did, we just did the antiderivative here times 10, the antiderivative here times 2, and then stuck a C at the end. That's the way I'm going to continue to, I'm going to do them in the future, but I want to show you like how the proper, why I'm allowed to just do it that way using the properties really intentionally. And talking about like what's happening with these constants. All right. So for this next one, we have cosine theta over sine squared theta. Uh-oh. Do I have an antiderivative rule that's going to allow me to deal with a quotient? Nope. What am I going to do? Yeah, there we go. So Tegan's got the right idea. He said, if I think about it this way, this is really the same thing as cotangent times cosecant. And that is on my antiderivative list. If I go up and I look for that, it is negative cosecant. And then I, of course, have the plus C stuck at the end. Feel okay there? If I look at example 3, what's different here? It's a definite integral this time, right? Is that going to change how I do the antiderivative part, though? No. So the antiderivative of x cubed is x to the 4th over 4. And I have minus 6 times. The antiderivative of x is x squared over 2. And then there's no C because it's definite. We're just going to evaluate from 0 to 3. So 3 to the 4th is 81. And then 3 squared is 9. And over 2 and times says it turns into 27. And if I do 0, so whatever that is, I don't care, was a 108 is over 4 is 27. So that's going to be minus 27 over 4, I think. Not bad mental math for 9:41 in the morning. Okay. Let's try another one. So again, definite integral, first thing I observe, and I'm just going to have 2 times, and then the antiderivative of x cubed is, great, and then minus 6 times the antiderivative of x squared over 2, plus, is there a constant on that last one? What would the constant be? 3. And what's the antiderivative of 1 over x squared plus 1? Tan inverse, yeah. Excellent. And again, no C because this is a definite integral.
So if it's indefinite, it's going to C.
Correct. 100%. Okay, so let's plug these in. That's going to be 8, and then 12, and then 3 tan inverse 2, and then it'll be minus 0 plus 0. Tan inverse of 0 is? Should be able to do this in your head. It is 0. Good job, Sophia. Again, the way I think about it is, if I remember what the graph looks like. 0, 0. So theta, comma, tan theta. Everybody's cool? So if I do that, what do I get? I have negative 4 plus 3 tan inverse 2. And if I needed, that would be like your no calculator answer. If you wanted anything more than that, tan inverse 2 is not something you could do in your head. So it'd just be and I got to make sure I'm in what mode? Radian mode for this. I just moved to degree mode last class. So negative 0.679. So either answer would be appropriate. Let's take a look at this next one. First thing I notice is it's a definite integral. Good. But can I take the antiderivative of the function as it's currently written? No. What's the trick going to be? What am I going to need to do to this function to massage it to get it something I can anti-differentiate? I'm going to write it as 3 fractions, all with the common denominator. Everybody's good there? And then along the way, I'm going to notice that this is really just t to the 2.5. Everybody's good with that? Okay, so now if I reduce each fraction, I have 2 plus t to the 0.5 minus t to the negative 2. And that's something now that I can integrate pretty easily. What's the antiderivative of 2? 2t. The antiderivative of t to the 0.5? Yeah, or you can write it that way. 2/3 would be fine, though. That'll make life easier in a moment. The antiderivative of t to the negative 2. Everybody's good with that? Okay. And then I just evaluate this from 1 to 9. So at 9, I have 18 plus... Okay, should be able to do that part without a calculator. What's 2/3 9 to the 1.5? Here, we'll make it easier for you. We'll write 1.5 as 3 over 2. So 9 to the 1/2 is?
18.
The whole thing is going to be 18. Good. 9 to the 1/2 is 3. 3 cubed is 27. Divide by 3 is 9 times 2 then is 18. Good. And then we have plus 1/9. And if I plug in 1s, I'm going to have minus 2 minus 2/3, and then minus still 1. And then I'll let you guys handle the arithmetic. Taylor.
Why is it -2 and then -2/3 and then -1?
Because I'm doing like f of 9 minus f of 1.
Oh, so then minus 2. Okay.
Yep, exactly right.
Just because it was a plus in the original. So it's just,
Nope. Totally fair question. Like I've shortcutted a lot of stuff. So if you missed what I was doing shortcutting wise, like for sure ask. Because if it doesn't make sense now, it certainly isn't going to make sense at home when you're trying to do it by yourself, right? All right. Application. So what kind of problems can I solve with integration? What kind of real life problems can I solve with integration? Great. So if I have a rate and I want to find out how much quantity that has accumulated over time, I can integrate that rate function over the time interval to get the amount of quantity accumulated, right? So Tegan had said if I have a velocity function and I integrate over some time period, it'll give me the distance traveled-ish. What it's actually going to be giving you there is going to be the displacement. So you're going to not get the distance traveled out of that. You're going to get the position, the ending position. Now, if you're traveling in a straight line, that'll be the same as the distance traveled. But if you're just like walking back and forth from here to the door, it'll just tell you the amount of displacement from your starting position, not all the back and forth that you've done. Is that okay? So we have to be very careful that integration is not going to give you necessarily accumulation if the function can become negative and positive, right? If the function can become negative, then it's going to give you like a displacement rather than a accumulation. Is that okay? All right. So the way the text refers to this, instead of accumulation, they talk about net change. So the net change in distance is the same thing as displacement. The net change in, like volume would just be like an accumulation of volume, right? So let's look at an example here. So we have a particle moves along a line. So that its velocity at time t is yada, 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 measured in meters per second. Find the displacement of this particle during that time period and the distance traveled during this time period. So displacement versus distance again. Displacement, let's say that we're just traveling back and forth between these two values. And we do this. And then we turn around and do that. And then we do this. And we turn around and do that. The displacement there would be 2. The distance then that we traveled, though, would have been 2, 1, 3, 2. So that would have been 8. Everybody kind of see the difference between displacement versus distance? Okay. All right. So how are we going to find that now using our integrals? Well, the displacement one is easy. That's just our net change theorem. So we're going to be integrating from 1 to 4 our velocity function dt. And that velocity function was just t squared minus t minus 6 dt. So the antiderivative of t squared is t cubed over 3. The antiderivative of t is t squared over 2. And the antiderivative of 6 is 6t. So if I do that, 4 to the third is 64. 4 squared over 2 is 8, so that's 24 thirds. And then 6 times 4 is 24, which is 72 thirds. So our displacement would be negative 32 over 3 meters.
You wouldn't do like the one.
Oh, yes, I would. Thank you. Goodness gracious, Mr. Kulik. Minus 1/3 plus 1/2 plus 6. Goodness gracious. And now I'm just doing this in my calculator. Can I point out to you an easier way of doing this on your calculator? So one way you can do this is if you type your antiderivative into the y equals menu. So I can do that. And then if I do vars, y1 of 4 minus vars, y1 of 1. I get negative 4.5, and that's probably a little bit easier than trying to type all that stuff in, right? And I would be okay if you've gone straight from there to there. Like, that's not a problem. Like, if you show me the antiderivative and what you're evaluating at and then just give me the number, I don't need to see you, like, whatever. I just get used to doing that because, well, there's a non-calculator portion of the AP exam, so I want to keep modeling for you how you could go about doing these things without a calculator also. You know what I mean? All right. Oops. All right, so for part B then, we want the total distance traveled, right? So let's think about what's going on here. This is a quadratic, right? It factors to t minus 3, t plus 2. So like from negative 2 to 3, it's going to be below the x-axis. And then after that, it'll be above, right? If we're looking for the integral from 1 to 4, we're talking about those areas where, remember, this area is negative and this area is positive. If I want the total distance traveled, I need to count that negative area as a positive. Okay? What does that mean mathematically? What am I going to be doing then? How can I shift that part of my function that's below the x-axis to being above the x-axis? The absolute value. Yeah, so what we're going to be doing in part B is the absolute value, or the integral of the absolute value of v of t. Now, do we have a antiderivative formula for an absolute value of a function? No. So what we're going to do is we're going to take the part of my integral that's negative. What part of my integral is negative? 1 to 3, right? Based on the picture I drew above. And we'll just make that part negative. And we'll add to it the part of my integral that's positive. And we're just going to do them as two separate integrals.
But how can I find out that it's negative? Okay.
So what I did is I graphed that function. And that was the picture I drew over here. So it had x-intercepts at -2 and 3. And I know it opens up because the leading coefficient is positive. So I just sketched a little picture. So this section here from 1 to 3 is the part with a negative area because that's the part that's below the x-axis. Does that feel okay? So I literally just looked at the picture of my function.
Yeah.
Right? Could you have typed that into your calculator and figured it out?
Yeah, but like, why is it only 1 and 3?
Because the integral is going from 1 to 4.
Oh, okay.
Right? That's the only part I care about.
Okay.
Is of the part I'm integrating over from 1 to 4, what part of that was below the x-axis?
Okay.
That's from 1 to 3. Is that?
Yeah.
Okay. Great. Here's the nice part. We've already done the antiderivative for this, right?
Wait, Mr. Joel, a bit of a follow-up on that last one.
Sure.
Why 3 specifically? Not you could have done like 2 or 2.5 or something like that.
Because 3 is where the other x-intercept is. Everything below 3 is below or before 3 was below the x-axis. So I need to take all the negative parts and make them positive, all those negative area, and make it positive. So I can take all the stuff that's below the x-axis and negate that part. So again, this antiderivative is the same for each of these. It's the same thing I found in the earlier part, right? So I'm just going to do this in my calculator. So I'm going to have negative and then vars y vars function y1 of 3 minus yeah, I put the negative on the outside, so I'm just gonna I put a parenthesis. You'll see in a second, but yes, you could write it that way also.
Oh.
And then plus, and then I have vars y vars function of 4 minus vars y vars function of 3. So I get there 10 and a sixth. But notice what's really happening here. If I call the antiderivative cap F, what do we really end up with? So if you're doing this by hand, that saves you plugging 3 in twice, making that observation.
What?
I'm just showing you that what we did up here,
Yeah, but weren't that two X?
well, I have a negative here and a negative there. There's 2 of them. That's all. Is that okay? Okay. Let's do one more. So here it says figure 4 shows the power consumption in the city of San Francisco for a day in September. P, that's the y-axis, is measured in megawatts. T is measured in hours starting at midnight and asks us to estimate the energy used on that day. So the energy, watts is a rate, right? Physics people, what's a watt? Joule per second. Good job. I would not have expected everyone to have
No,
spit
but I
that.
am in physics, that's the problem.
Oh. Well, that was good timing on my part then, right?
Wait, what did physics?
So my total energy is going to be the integral from 0 to 24, right? That's one day. It says that starting at midnight, so 0 hours is midnight. P of t was my function that I'm graphing. That's the rate function for... Everybody's okay with that? Are we given a function for P of t, though? How am I going to do this then? I'm going to approximate this. How am I going to approximate this? I'm just going to count some boxes, homie. So let's see, that's a 4 by 24.
Do you think if they actually do this, they would count some boxes?
If you're given this, I mean, you'd have a computer program that would do, but from what you're given here, that's what I'm doing. Like on an AP exam, that's what they want you to do. They're like literally like we're counting some boxes here, homies. Actually, let's go all the way over. That's probably enough. One, 2, 3, 4, 5, 6. So that's 18 there. I'll do it the same way. Okay. So that is 2 less, 3 less. That's going to be a 15. And that's 2 less, 1 less. So that's going to be a 12. And then that's 3, 4 less. So that's going to be an 8. And then we have some kind of partial boxes, right? So let's see, this one, how much of a box do you think that is? We're just going to go from left to right across.
I'd say 1 if you count the one next to it.
Okay, you want to do those as 1? Sure. That seems reasonable. That's a decent idea, Paul. And we probably count these 2 as 1. You guys buy that? And those 2 we can probably call 1. And then what do you think about these 3 we can probably call 1? And then those 4 is probably 2 total. And I don't know, these 2 we can probably call 1. Those 2 we can call 1. And those 2 we'll call 1. Everybody agree with that? Now, that's how many boxes we have, but we have a little bit of a units issue going on. How much is a box? So this is, a box is 100. So we have, each box has an area of 100. Everybody agree with that? So we'll multiply that by 100. And we also have a units issue going on. So watt is joules per second. Our time is measured in hours. So we have to convert these times to seconds. So I need to multiply this then by 1 over 360, right? Or 3600. That'll get everything into seconds. So whatever this is, whatever that number then is megajoules. Since we're in megawatts, I forget what the exponent, the scientific notation for mega is. Is it 12th? I don't remember. But that's how I would approach that problem. Is the tricky part is remembering to do this stuff at the end after you've counted your boxes. It's to the 6th? Okay, so we could do that. Now, on a test or whatever, I'm not going to be this big of a jerk. I'm going to give you units that you know what they are. Like I wouldn't say megawatts, I would say like joules per second, right? I would just give you the rate, not as an SI unit, but like in its component units. So that's obvious what the unit is. If you have to do a conversion, what you'd have to do. Everybody's okay with that? Wait a minute. This should be times 3600 though, shouldn't it? Not 1 over 3600. Like 1 hour. I should multiply by 60 to get to minutes. That's my bad. That'll convert those hours, which are all of these units, are all hours. What do you guys think? This section is a lot like the previous one, right? Like kind of a big nothing burger. But like, all right, no biggie. So we'll close this down for today. Next section, we're going to look at 5.5. That's the last section in this chapter. Oh my goodness. It's also probably the trickiest one in the chapter. Not from a computation standpoint so much, but like what we're going to do is we're going to learn how to find the antiderivative of chain situations. So if I had to differentiate using the chain rule, and I'm now trying to put this back, what is that going to look like? How do I do that? That's what we're doing in section 5.5. Next time we'll also do the homework quiz. So the homework quiz is going to be 12 my AP multiple choice questions. We're going to do it in class, no calculator.
Wow. Yeah, that's gonna be.
Okay?
Can we use Google?
No. Here's the deal, though. Like, the calculator,
Do you even need a calculator?
not really.
Okay.
Not really. I don't think so. The questions I picked, like, you'll have some, like, whole number multiplications and additions that you'll probably have to do. Which, okay, that's, like, annoying to do without a calculator, but totally doable for me. And then things that it's like, well, this is all symbols here anyways. What am I going to do with the calculator with this anyways?
And what section is that?
I'd say through 5.3.
Okay. So nothing with like indefinite.
Correct. At least that was my memory of putting it together when I did it. So again, things that you'd want to make sure that you remembered for this, right? Because we covered a lot of theory along the way here, right? You're going to need to know all your antiderivative rules. If you don't remember those already, you need to have those. Like, they can't go away. You have to have that memorized. You need it. Your properties of integrals, like, oh, okay, I can distribute an integral across addition, or I can pull a constant out front, or I can take a definite integral and break it into pieces, or if I flip the bounds, it makes the integral negative, like those little properties. Again, you don't have to be able to write the property, but you just have to be able to use it in context. Or even that one that we looked at in the homework problem, whatever, 76 or whatever you guys asked about. Like this one here, where if I have, like an upper and lower bound for a function, I can like, if I integrate both sides, I get the upper and lower bound, or the integrals are bounded, like we did in 7.3. Like that's a good one. Or in 73, we just did this, right? It's this one, 73. Like this property that I used in 73. That's a good one, especially for like show that this is a da-da-da-da, or like which of these is true. But it's otherwise the questions are on your own, or we'll put a time cap on it. So like 30, 40 minutes, something like that. So a couple minutes per question. So you can't take all day long thinking about it. But they're multiple choice too. So like if you can knock out a couple of guesses and you have to guess, that's not the end of the world. But I also want to start at this point like practicing our time management for stuff. I did these after I picked them. I think I took like about a minute per question. None of them are like require like a page of writing to figure out. Now again, like this Mr. Kulik, one, I picked the question so I kind of knew what I was looking for. Two, this is not that hard for me because I've done this a lot of times. But like a conversion factor of like 3 or 4 to 1 time-wise is probably pretty reasonable for you guys. Okay? So just giving you a heads up about like the format for this, because it's a little bit specific here, right? It's not just like, here's some stuff on a paper, like use whatever you got, because we've done a bunch of different things before, right? I do want to do a little bit of start working in some more multiple choice practice, because we don't do much of that. Most of this work we do in the class is like problems and like worked out stuff where you can get partial credit and stuff from it. It's not quite as cruel as the multiple choice where it's like yay or nay.
Yeah.
And then we don't do a lot that's timed either, So I want to start working a little bit of that practice in. Paul?
Would you be so kind to make us a review for the test?
I did make one for the test this time, like a real review, because I had enough things that settled a little bit more, so it wasn't quite as chaotic as first semester has been. So, Teagues.
Is the quiz going to be graded out of 12?
Well, no, I'll have like, we'll figure out some banding.
Okay.
Like, not, you don't need 100% to get a 10, right? Or a 12 or whatever we make it out of, right? I'll probably make it out of 10 and just like, 75 or better is 10 and so on, which feels probably pretty fair, right? Give you a couple of, you can whoopsie a couple of them because, well, it's timed and there's no calculator and they're not that easy. I mean, when you're seeing it for the first time and you don't know what to expect, it's not that easy, right? So, again, you don't have to be perfect. And that's one of those things I want to hammer away again prior to the AP exam is like, if you feel like, boy, I failed that, you might have gotten a 3 or 4 still. Like 50-ish% is kind of in that 3-4 range. Like that's real good. So I don't want you to guys, like, it's very easy to get disheartened where it's like, I don't know any of this. Like, I'm just getting, like, I failed that. It's like, this might have been okay. It might have been okay. Don't quit. Don't quit. You'll surprise yourself. Sophia, you thought you took the AP stat exam. You told me you thought you failed it. What did you end up getting? A 4.
That was just luck.
It wasn't luck.
It was.
You knew way more than you thought you did. And that's okay. And again, it's not going to be perfect. It's not going to feel like a test where it's like you got done and like, oh, I basically knew how to do everything. I probably got an A. It's like, boy, I didn't know how to do a lot of stuff. And you can still get like an A. Like you left questions blank. Yeah, that's fine. That happens. Yeah, that's going to happen. You may run out of time. You may just have no idea what to do with it. That's okay. Just don't quit. Try to do everything you can. You'll surprise yourself. And I don't mean to pick on you, Sophia, but you told me that. I figured it. Yeah, I figured that would be okay to share with everybody.